Hey guys, in this video we are going to discuss about the photoelectric effect. Now before we go to the definition part, let us see what actually happened and then draw conclusions, and then we can go to the definition part. So for a given setup like this, when light was incident on a metal plate, current was observed in the external circuit. What was observed further was that when the frequency of the light was changed, let us say we start at the extreme around further beyond long radio waves here, and as we move towards increasing the frequency, that is towards microwave, infrared waves, no current was observed. So the electrons were taking the energy, but it was not enough for them to leave the surface and create a current. So once a particular frequency was reached, let us say 10 to the power 14 Hz, the current was established in the circuit. Furthermore, when for this particular frequency the intensity of the light was increased, more current was observed. So based on that, the photoelectric effect can be defined as the phenomenon or the phenomena of emission of electrons from a metal surface when radiations of suitable frequency is incident on it is called photoelectric effect. So let us say you have the incident light having the frequency HF. If you incident it on a metal plate, electrons will be ejected from the metal surface. This phenomenon is called as the photoelectric effect. Emphasis on the word suitable frequency. It doesn't happen for all frequencies. For each metal it will happen for a desired or a definite frequency. Let us see some terms related to photoelectric effect. Work function. Now the electron requires a minimum amount of energy to leave the metal surface. That energy, that minimum amount of energy is called as its work function. Threshold frequency. The minimum frequency of light which can eject photoelectron from a metal surface is called threshold frequency of that metal. That means below that frequency you will not see the photoelectric effect. Now we know that wavelength and frequency are inversely proportional. So if you go on increasing the wavelength, that means you are decreasing the frequency, again you will not get the photoelectric effect. So the maximum wavelength of light which can eject photoelectron is called as the threshold wavelength of that metal. Now, based on the definitions, we can have the relation between work function, threshold frequency and threshold wavelength as phi. That is the symbol for work function as equals to HF0, that is Planck's constant times the threshold frequency, or C divided by lambda max, that is the relation between frequency and wavelength. Frequency and intensity are two properties of the incident light that affect the photoelectric effect. Frequency is related to the energy of photons. We already know E equals to HF. Higher frequency means high energy. The intensity relates to the number of photons. So, if you have higher frequency, you have higher energy photons, while if you have more intensity, you will have more number of photons. That means increasing frequency will increase the kinetic energy of the ejected electrons. They will absorb more energy and they will have more kinetic energy while they are moving. While increasing intensity increases the current in the circuit. So there will be more electrons that are moving with the same energy. So we can conclude that for a given metal and frequency of incident light, the photoelectric current is directly proportional to the intensity of light. So the current and intensity are related. For a given metal, there is a certain minimum frequency called threshold frequency, below which emission of photoelectrons doesn't take place. So you need to have a minimum frequency requirement met. Then above threshold frequency, the maximum kinetic energy of the photoelectrons depend upon the frequency of the incident light. Once you cross that threshold frequency, you can have more and more kinetic energy by changing the frequency of the incident light. and the photoelectric emission is an instantaneous process. So as long as the light of proper frequency is incident, you will have the photoelectric emissions. Once you turn off the light, the emissions stop. There is no delay in this process. Now work function and kinetic energy. So since we have established some definitions, let us relate them by equations. You incident HF amount of energy. The part of the energy is used by the electron, that is the work function, to leave the metal surface, and then the rest of the energy is utilized as kinetic energy. So HF will be phi plus Ke, kinetic energy maximum, or HF0 plus half mv square. We know the rule for kinetic energy. Or we can also find kinetic energy by rearranging the equation. Kinetic energy maximum is HF minus HF0, or taking out H common, the bracket F minus F0. Similarly, we can have the same equations for lambda. So instead of frequency, we can put C by lambda. Hc can be taken as common. So 1 over lambda minus 1 over lambda cutoff for F0. Let us solve a problem using these equations. A piece of metal has a cutoff wavelength of 450 nanometer. Consider illuminating this piece of metal with two different wavelengths of light, lambda 1 500 nanometer and a lambda 2 400 nanometer beam. For each of the two beams, find the maximum kinetic energy of the ejected electrons and what is their speed. Now, there are two wavelengths, but the cutoff wavelength is already given. By definition of cutoff wavelength, we know that once you go above cutoff wavelength, you won't get the photoelectric effect. So there is no point of doing these calculations for 500 nanometer because it is above our cutoff wavelength. So we'll be solving for 400 nanometer beam. So we use the rule. Kinetic energy is HF minus phi. So H is Hc by lambda 2 minus Hc by lambda cutoff. Take out Hc common. Substitute the values for H, the speed of light in vacuum, and our wavelengths in nanometers converted to meters. Simplifying this, we get the energy as 5.21 times 10 to the power negative 20 joule. Now for the second part, for finding the speed, we know the rule for kinetic energy is half mv square. So rearranging this, we get V is square root of 2e by m. So put the values. M is the mass of an electron, 9.11 times 10 to the power negative 31. Simplifying this, we get 3.58 times 10 to the power 5 meter per second.